Hello, this is Dr. Strickland. In this video, we will review significant figures. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. So analytical chemistry is based on measurements that provide information in fields such as medicine, environmental chemistry, forensics, and the production of every consumer product on the planet. But the uncertainty of a measurement is as important as the measurement itself because it tells us how reliable the measurement is. The repetition of one type of measurement several times tells us the reproducibility or the precision of the measurement. Measuring the same quantity by different methods gives us confidence of nearness to the truth, that is, the accuracy of the measurement, if the results agree with one another. So the first thing we need to be able to do is to read a measurement from an instrument or a piece of volumetric glassware correctly and get every bit of information that we can, because all of the information that's reliable is significant. It tells us something important. All right, so the first thing you want to do is find out what the graduations mean. Like, for example, down here with the absorbance portion, how much absorbance is represented by the distance between two lines? So like if you see these major divisions like 0.1 to 0.2, very often there are 10 graduations between the major marks. And that's true here. Now, when you want to read an absorbance, you also need to know, does it increase left to right or right to left? And in this case, it's right to left. And you can see that this measurement is between 0.23 and 0.24. So it's 0.23 something. And so that something is the final significant figure in the measurement. There's a measurable amount of uncertainty in that final digit caused by interpolation and assumed to be 1/10 of the smallest division, which means that I can tell the difference between 0.231 and 0.232 and 0.233. And so if I was reading this one, I would say that the absorbance was 0.233. The absorbance is represented by a capital A, and it doesn't have any units. Now, if you look on the percent transmittance portion, we see that the numbers increase from left to right, that each one of these little divisions here represents a single percent transmittance, and this percent transmittance is between 58 and 59. So it's 58 point something. So the percent transmittance, I think, is 58.2%. Now you might say 58.1% or 58.3%, and we would all be within this 1/10 of the smallest division. All right, so once you have your measurements, you have all of the significant information, all of the significant figures that you're going to get. But very often measurements are combined to calculate other quantities, to test different variables, to look for different relationships. All right, so technically, the number of significant figures in a measurement is the minimum number of digits needed to write a given value in scientific notation without loss of precision. So it's everything that we were just talking about. And you know the rules for determining significant figures and whether zeros are significant or not. If you don't remember those well, it would be a good idea to go back into Chapter 3 and just go through that. But what I want us to focus on now is handling them in calculations. So we're going to look at the rule for significant figures in addition and subtraction, and then we'll take a look at it with multiplication and division. Now you know that the number of significant figures in the answer to an addition or subtraction is controlled by the factor that has the fewest number of digits past the decimal. So one thing that's handy is to line them up. So if I took 22.98976.928 and stacked it with 35.7 453. And you don't have to stack them. I mean, people put them in their calculators all the time. But this lets me show you that this factor, which has only 3 digits past the decimal, is the one that's going to control the number of significant figures that I can keep in my answer. Because there are going to be a whole gazoodle of numbers down here. But whether those numbers tell us anything important or not is the province of significant figures. All right, so this answer is 58.442. And then we've got this 76928 hanging on. And then the question, of course, is you look at this and you find out if it's okay the way it is or if it needs to be rounded up based on what comes next. And that's another one of those rules that I want you to look up. So the answer here is going to be 58.443. Sorry, 0.44, yes, 3. And then the units are AMUs, atomic mass units. Now, it's also true, and we'll talk about this a little bit later, that if you're going to take this answer on in a further calculation, we're going to keep something called a guard digit, but we're not going to do that for right now. All right, so with scientific notation, if you're going to add 2 factors, add 2 quantities that both have an exponent like this, one of them's got to be changed. And so we've got, in the first one, we've got 10 to the 6th. In the second one, we've got 10 to the 4th, and you can decide which one you want to choose. I decided I wanted them both in 10 to the 4th. So if I'm going to make the exponent smaller, I've got to make the number bigger. And that means the decimal slides 2 digits to the right. So this is 256.9 times 10 to the 6th. I'm sorry, times 10 to the 4th plus 4.002 times 10 to the 4th. All right, so since these are both the same, that will be the exponent here, at least for the moment. When I add these, I can only keep to the 10th place. So 260.9, and then the O2 is kind of left over. If I'm going to put this into proper scientific notation, then I've got to move that decimal back until it's just to the right of the first digit. So that'll be 2.609 times 10 to the 6th. All right. Now, multiplication and division are different. The number of significant figures in the answer to a multiplication or division is controlled by the factor that has the fewest number of significant figures. So if I look at this one, it's got 4 significant figures, and this one has 4, and this one has 3. So that tells me that I can keep 3 significant figures in the answer. So when I do this division and then the multiplication, I got 1,622.55448, which is an impressive amount of digits, but I can't keep them all. I can only keep 3. So that means these 3. Okay, which means that the answer has to be written like this without a decimal point, which tells me that that 0 is a placeholder, but it's not significant. Now, if you do have scientific notation, when you divide 2 factors that both have an exponent, you're going to subtract this exponent from that one. Multiplication, you just add them together. So here, I got 0.731844746. Again, an impressive number of digits, times 10 to the 18th. But I can't leave it like that. I'm going to have to move it over there, make the number bigger, make this smaller. So, and I can only keep, well, let's see, 5 significant figures there, 2 there. So I can only keep 2. So it will be 7.3 times 10 to the the 17th. All right. So that is the basic story on counting significant figures, where they come from, how you handle them in basic mathematical operations. If you have any questions, please send them to me.